Yeah. Thank you very much for that very nice introduction. Yeah. So ML is actually the very first typed functional programming language that I learned. So I was very happy to be invited to give this talk. And now the thing about ML is that, you know, I said, oh, it's the first typed functional language that I learned. And when we teach students ML, we tell them this is a functional language. You should use data types and pattern matching and inductive reasoning about your programs, and then you will be in a very happy situation. And this is true, but ML isn't really. Like, it supports things like this function right here. So what this is doing is, this is the famous Landon's knot that Peter Landon invented, which implements recursion by backpatching. So we have this function f whose fixed point we want to take. Like, suppose we want to implement factorial, we could write down the recursion scheme for it, and then what we can do is we can say, well, let's allocate a reference which points to some dummy function, and then define a fixed point by saying, oh, I have a typo there. It should be f applied to x, which dereferences r, and then applies it to x. So this here should be bang r applied to x. So look up in the heap what function is here, and then apply it to the argument. And then we can implement the recursive function by assigning the reference to the very fixed point function which we just defined, and then we can return it. And now we've implemented recursion, and you can see there's no Y Combinator in sight. This is the kind of implementation of recursion that a C programmer would be happy with if they could conceive of such things as function pointers. And so this is really a very, very imperative program. So, you know, you can see this rough constructor gives us a pointer, and it's not just like a pointer to an array of floating point numbers like a Fortran programmer might want. It's a pointer to a piece of code, and it's not just a pointer to a piece of code the way a Java object is. It's a pointer to a piece of code that we dynamically modify. And if you try to reason about these programs, you'll quickly realize that this is really hard. Like this 4-line program was, I think, like Peter Landon came up with it in the 60s, and we didn't really have good proofs of its correctness until just a few years ago, like 2010, 2012. So it took like almost 50 years of thinking before we could even begin to start proving the correctness of programs like this. And what I'm going to do is I'm going to try to argue that this kind of thing is actually a good thing. So it's extremely difficult to reason about, but it'll also turn out to be extremely useful. And it shows up a lot, this kind of pattern of dynamically modifying higher order code shows up a lot in graphical user interfaces for reasons which we'll see in a bit. So first let me motivate why you might even want to consider like verifying a graphical user interface. So it turns out that these graphical applications like user interfaces are very easy to get wrong. So a few years back, Adobe did a study of their projects to identify like what the sources of problems in their code base were. And they found for applications like Photoshop and Illustrator and Elements and things like this, that about 1/3 of their code was dedicated to UI event handling. So this is things like what to do when a button is clicked, how to select things, how to drag and drop things, like the basic UI interactions. And they found that, you know, this UI code was about 1/3 of the code base, and it represented the majority of their bugs. So that is to say that like clicking and dragging was harder to get right than high performance image processing code that's like extremely mathematically sophisticated and implemented in optimized C++. So that's really peculiar. And when you see the kinds of bugs that they had, so here's an example bug. So here's a save image dialog from one of their applications. You can tell the age of this bug example from the UI style of macOS here. you can see that they have, you can save this this picture as a JPEG, and JPEG is a lossy image format, so you can throw away some information in order to use less space, or you can choose to have a bigger file size and compress with higher fidelity. And so they just have some sliders, so you can set the quality and compression ratio to adjust how much you want to make this particular trade-off. And on the other hand, there are also lossless image formats like PNG and GIF. And if you save an image as a PNG or a GIF, you don't need these sliders. So the idea was that if you change the file type to a PNG, then those compression ratio sliders should go away. And obviously the bug was that they didn't. So you would switch the file type, and then the sliders would disappear or not. Like, it actually depended on the exact sequence of operations that you did, whether it went away or not. And this is a very, like, it's not a complicated conceptual bug. It's just some piece of very simple logic that they just couldn't happen to implement right. And this is quite peculiar. And you might think, okay, who cares if there's a slider that doesn't do anything? But like, interfaces are how we interact with computers, and so we rely. And nowadays, every computer I have talks to the internet and stores all my personal information. So here's a screenshot of some of my personal information. So so this is a Gmail popping up in a web browser, and what you can see here, let me see if I can highlight it, is I just got some email from my mother saying, please send me your address so that I can send you some money or receive some money. And like all my bank details, enough to completely empty out my bank account, or put things into it, I hope, will be sent over this kind of connection. And in order to trust that this is a secure connection, what I do is I rely on my web browser to be secure. And I suppose I want to send her some money, I'll go to my bank account, and then I'll fill in my details. And to know that this is a safe thing to do, I'll look at the URL bar, and I'll say, aha, I see this little lock icon here. That means that I can trust that the TLS encryption is going on. Obviously, there is no possible way I could actually look at the bytes being sent over the network and decide whether it's encrypted or not. Well, I guess I could if I had Wireshark, but I don't. And the thing is that a browser is essentially a program to let the internet draw on your screen. So this is a screenshot of the Kronos group, which is the organization that maintains the WebGL standard. And this is a demo of their one of their demo pages. So you can see what looks like an ordinary web page, and then you can do something like tell OpenGL to draw things on your screen. Here's the famous OpenGL teapot. And, I can draw all kinds of cool teapots. So how do I know? And how do I know it can't fake the toolbar? Especially since browsers are used as sort of application engines, and so they support features like going into full screen mode. So I go into full screen mode, GL is doing its thing, and I decide to go out. And I see all these browser decorations. So now the question is, how do I know that that's the real browser menu bar and not something that OpenGL has been drawn using OpenGL by a malicious website? So is this real or not? And in this particular case, we have some confidence that the obvious attack doesn't work, because browser engineers thought about it, and when you go into or out of full screen mode, the browser will pop up a modal dialog saying, you're about to go into full screen mode. Remember that unless you explicitly go out of full screen mode, someone can fake all of the security UI that you rely on. And so that's the way they mitigate this attack. They'll give you some information and hope you remember it. And so this is very important, and it's also really easy to get wrong. So it's like sort of a bad combination. I guess it's like easy to get wrong, ubiquitous, and important, which is like sort of like an infernal triad or something. And so the thing that makes GUI programming hard is actually the fundamental programming model that most GUIs expose to the client. So the model they expose is what's called an event loop. So here's this event loop, and what it is it's a big while loop that waits for events to happen. And these events are things like mice being clicked, keyboards being typed, and these days things like motion sensors and cameras and speakers and things like that. Basically any kind of event that can come from the outside world or the user into the program. And I guess it could also be things like more computer-y events like network sockets sending you data and things like this. And to react to all of these events, what programmers do is that they install a bunch of callbacks into a table, and this big while loop will wait for an event to happen. And so this get event function is going to wait for an event to happen. And then on the event, when an event is actually delivered to the system, the event loop will wake up and it'll look in the table. So suppose that a key is pressed. What will happen, it'll say, okay, let me look in this table, and now, there's a bunch of functions here. Let me load these functions from this event table, and now let me just iterate over them one by one and execute each of these bits of imperative code. And then I'll go back to the beginning of the while loop and wait for the next event to happen. So, this is, a reasonable model. It was invented the year I was born, and it's still used today, so it must have something going for it. But if you look at it from the perspective of a semanticist or a type theorist, this is really insane. This is a higher order imperative concurrent program written in like sort of continuation passing style, where you store the bits of the continuations in a table that you dynamically modify. And any one of these adjectives you could get a PhD thesis out of. And somehow we are in a world where regular programmers are expected to deal with them all at once, and with disastrous consequences if they get it wrong. So let's see, like naturally the question to ask is there a better way? And almost 20 years ago, Paul Hudak and Connell Elliott had this thought, well, this is really hard to reason about it, so let's not. Let's think about interactive programs in a different way. So what we'll do is we'll view dynamically varying state not as a pointer in memory which we bash on, but rather we'll view our time-varying state as a stream. So here's a stream C's, which at time 0 has W, at time 1 has O, at time 2 has R, at time 3 has L, and time 4 has D, and so it evolves through the word world over time. And now if you view this, if you view state as a stream, then an interactive programming is a program is a stream transducer that takes streams of inputs to streams of outputs. And the nice thing about stream transducers is that we can define them recursively. So here's a function that will take in a stream of numbers and then double them. And so you can see it looks like a perfectly reasonable functional program. We take the head of the stream, double it, and cons it on to a recursive call of double on the tail. So that's a very easy program to reason about. And so now we have all the standard functional programming primitives, like we have a type of streams, and we can take the head and the tail of a stream, and we can build new streams using cons, and we have functionals like map and unfold and zip and unzip, and we can build up stream transducers in a very elementary style that you can reason about very easily. And so you think, okay, we have really nailed this problem. And if you look at Elliott and Hudak's original '97 paper, like all of their programs are just beautiful, like, you know, extremely sophisticated animations can be specified in a handful of lines, and, you know, that it's not just a specification, you can actually run it. So it looks really beautiful, and, you know, for the past 2 decades, like dozens, maybe hundreds of people have all thought this is really the way to do it. And then when you try to actually use it, you discover that when you get it right, it's perfect, but when you get it wrong, it's really hard to tell. So here is a example of the sort of problem that that you run into if you take this stream transducer model of functional reactive programming. So I have a stock trading program here, defined as a function which takes in a stream of prices and emits a stream of buy and sell orders. And so what it'll do is it'll say, aha, I have a stream of prices, and if today's price is less than tomorrow's price, then I'll buy some stock, and if it's less than tomorrow's price, then I'll sell. And because I'm not giving this talk from my own private island, you can tell that this can't be implemented. So actually, I should say the situation is slightly worse than that. You can implement it, and if you try to run it, if you are lucky, your program will go into an infinite loop, and if you are unlucky, it'll wait until tomorrow to decide whether to buy or sell, and all of your buy and sell orders will be sort of off by 1. So the thing is that mathematically, this is a perfectly fine function on streams. It's perfectly well defined. It's just bad as a kind of model of interaction. So the thing is, it's violating not a mathematical constraint, but a sort of physical or temporal constraint. It's violating causality. It's trying to use information from the future in the present. And so so now the thing is, you know, I'm a type theorist. So when I see these kinds of constraints, I think, okay, well, here's a constraint in this program that the type system isn't capturing, so let me extend the type system. So what I'm going to do is I'm going to say, well, here tomorrow's price is just a stream according to the typing rules for tail. So what I can do is I can change its type. And here's how we can do that. We can say, here are the types of streams, head and tail and so on. And what I can do is I can add a new type type former to the language. So I can add this type, which I write bullet A, and we can pronounce it as A tomorrow or next A, and it denotes the type of values that are available tomorrow. So if an int is an int that you have right now, a next int is a computation that when you run it tomorrow will give you an integer. And so now we can use this new type to change the types of all of these FRP primitives. So what we'll do is we'll say, taking the tail doesn't give you the tail stream, it gives you the tail stream tomorrow. So on the next step, you'll get a stream. And then what cons does is it'll say, well, you can't just cons an element in a stream, you have to cons the head of the stream, which you have right now, and a tail stream, which is a stream starting tomorrow. And then, because one of the big problems in reactive systems is the issue of causality, we can say, well, we want to define these stream functions recursively, but we want to make sure that when we feed output back into the input, we only want to use it later. So we'll say, we'll change the type of the fixed point operator and say feedback has to operate through a delay. So if you have a function that takes a next A to an A, then you can take its fixed point, but not otherwise. And if you do this, it's possible to prove that you now have a well-founded model of reactive programming that's completely deterministic. And so now we have deterministic programs that are all causal by construction, and you'll never get an infinite loop or a causality violation, and everything you can define works the way you want it to. So that solved the problem of causality, and I worked out a calculus for this in like 2011 or 2012, and I thought, yeah, I really nailed this problem. And then I implemented it, and then I wrote programs that worked great, and then after about 10 or 15 minutes, like, my whole system got sluggish, and then everything crashed. And the reason was that I was writing programs that were leaking a lot of memory. And these leaks were like quite subtle to diagnose. So in the FRP literature, these are called space leaks or time leaks, and diagnosing them can be very tricky. And you can see an example of why it's so tricky. So here are two constant functions. So a constant function just takes an element and repeats it infinitely often. So these programs are identical. So const x takes is at the type nat arrow stream of nats, and what it does is it says const x conses on x to const x. So we're recursively defining a stream. And const ends takes a stream of natural numbers and produces a stream of natural numbers. And these programs are absolutely syntactically identical, well, up to alpha equivalence, and the only difference is in the types. And the program on the left leaks and the program on the right doesn't. And so we think, okay, now how can we distinguish them? And again, this is a case where we sort of have to look at the operational semantics or the operational model of reactive programming to figure out how. So the thing is that once we add time to a programming language, like, values have extent not just in memory but also over time. So the idea here is we have n's on the left, which is a stream, and n on the right, which is a value, an integer. And the idea is we have this stream which successively enumerates the natural numbers, and at time, and the double circle on the left is the value at the current time step. And so the idea is that at time 0, this stream will produce a 0, at time 1 it'll produce a 1, at time 2 it'll produce a 2, and so on. And you can see that the sort of this program is this value is changing over time. Like, its value is changing over time. So it's 0, 1, 2. Like, you can think of it as a state machine whose state is changing from 0 to 1 to 2. But 3 is pretty simple. It's going to be like what would it be, like 1, 1 in a binary word. So, 2 bits in a word somewhere in your heap. And so the thing is that n is something that's constant over time. It doesn't change, and n's does change over time. And to represent this change, you have to use memory. And so now we can understand why const of n's leaked memory. So if we try to let me go back to the previous slide and I'll show you. So there, here's the leaky program const, and what it's doing is it's saying, I'm going to replicate this stream both at the current time and at the next time. So what this means is that const of n's should return 0, 1, 2, 3, 4 at every time step. But the data structure n's that we have is changing over time. And so that means that we have to save the first few values of the stream in order to be able to reconstruct the mathematical stream that we want to return. So if we want to return a constantly 0, 1, 2, 3, 4 stream at time t, we have to save the first t values of the stream and then return that tth tail along with it. And so that means that it's going to use O of n memory. And this is why why the programs that I was using were running out of memory so quickly. It's because they were using O of n memory when n was increasing by about 60 every second. Actually, I guess if I was using higher order functions, it might have been O of n squared, where n was increasing by 60 every second. So in other words, like after 10 or 15 minutes, things were bad. So what we can do is we can say, well, we have this distinction between things that change over time and things that don't. And things that don't change we are safe to use whenever you like, but whereas things that do change over time, we want to say they're good on a particular time step, but don't try to refer to them later, because I'll have to remember a bunch of facts which will use up my RAM. And so what we'll do is we'll add a new type constructor. So you can see the type theorist at work. Like, I have a problem, let's add some more types. And so what we'll do is we'll say, okay, I'll add a new type, box A, which are the type of stable A or always A. So these are the elements of A whose representation does not change over time. And some types, like natural numbers, all of their inhabitants will be stable, and other types, like streams, none of their inhabitants are stable. And at function type, some are stable and some are not, depending on what a closure captures. And so, yeah, that's just what I said. So all elements of n are stable, no elements of streams of n are stable, and some elements of A arrow B are stable. And so now we'll just go through and add some more boxes to these types. So the type of fixed points, we'll say we can only take a fixed point of a recursive function if that function is stable. This is because this loop is going to execute on many different time steps. So you can imagine the recursive call to const happened again and again and again on time 0, 1, 2, 3, 4. And so since we want to call this function at many different times, we're going to stick a box on it. And then we can go through and adjust the types of the various functions. So like map is also going to be you can only map a stable function over a stream, because again, when you write map f, that f is going to be called at many different times. Okay, and so now we've made the following changes, and now we can say, let's write down a function const which takes a stable A and then produces a stream of A's. And so now we can say I have a constant stable A. I get a stable A as an argument, and then I can cons A onto a recursive call to const box A. So this thing, where is this? So this thing here is the pattern matching elimination for it, and that's the introduction form. It's just a syntactic marker telling you when you're going into and out of a box type. And I'm not going to show you the typing rules for that. Okay, so now this can be called if that type A is of type natural number, because we'll be able to make natural numbers into a stable type, embed them into a stable type, and we can't call it if A is stream of natural numbers, because there aren't any stable streams. And so now that solves the problem. And yes, Ralph?
If I still wrote the old Leaky program where it didn't have the box, how would it get rejected?
Yes, so the question was, if I wrote the old leaky program, what would happen? So in this particular case, you would be able to write it. It would say, if you give me a boxed stream of natural numbers, I'll return a stream of natural numbers. And that would pass the type checker. It's just there are no inhabitants of box stream of n, and so you'd never be able to call the function.
Let's take it apart.
Okay. So yes, so the point is that that these stable markers tell you when you can use a value at multiple times, and the invariant of the correctness proof is that only stable values get used at multiple times, and we can actually implement it, and it all runs all fine. So I said the word implement, so let me show you how you do implement it. So I said, you think of next A as a kind of delayed evaluation. So it's sort of like a thunk in Haskell, only you actually schedule its execution. So a next A is a piece of code that we're going to evaluate tomorrow. And so we'll represent it as a pointer to code. So it's going to be a thunk type. So it's going to be ref of unit arrow A plus A. And so we'll force this thunk on the tick that it's scheduled to run, and then we'll replace the thunk with its value after we do execute it in order to avoid recomputing these thunks over and over again. And here's the tricky bit, after the, on the time step after its lifetime ends, we'll just null out the pointer. And this will throw away, very old values, and therefore, by construction, we will never have a space leak. So a priori, yes?
Can you set it up for the garbage collector to collect this, or collect that pointer after it's done with it when it goes out of scope, or?
Okay, so the question was, can we set this up for the garbage collector to collect after it goes out of scope? Yes, we can, and I'll show you how that works on the next slide. Yep. So what will happen is that, we're nulling out these pointers in order to make sure that after the time step A is supposed to be live on ends, we no longer have a reference to the value. And so we sort of know by construction that there are no space leaks. And this is great, like it's an obvious guarantee there are no space leaks, but it's not an obvious guarantee that there are no null pointer exceptions. Because this next A is a pointer to a piece of code that we're going to null out. And luckily it's possible to prove that that this implementation technique works. So what I did was I said, okay, well, we have a language with higher order functions and mutable state, and so what we can do is we can use some of the techniques that have been developed over the last decade to reason about higher order languages with state to actually verify this implementation. So I use like nominal step index scripty logical relations. So these are techniques that people like Andy Pitts and Derek Dreyer and Amal Ahmed have developed to like a very high degree of sophistication over the past decade. And I would say yes, it is a fairly complicated proof technique, but the benefit of this is that this is a complicated proof, but we only have to do it once, and the programmer never has to do it. I have to do it in order to verify that the proof technique works, and you would have to do it if you wanted to implement a similar kind of language, but it would be a once and for all kind of proof, just to establish the correctness of this implementation technique. And so in addition to this, we get a host of very strong guarantees. So now we have no space-time leaks in this in any definable program. There's no causality violation. So every program that's definable in this language is causal, well-founded, deterministic, and doesn't leak memory. So it has a very good semantic properties, and it also has very good operational properties. So we have all these fancy types. One question, you might ask is, okay, well, you've put in a whole bunch of types following this type theoretic methodology, but can we explain it to the programmer in any way? I've added these types to the typed lambda calculus, and I've explained them to you in terms of these operational intuitions about thunks and memories changing over time. Are we just sort of dumping a bunch of work on the programmer that they can't understand? Do these concepts make any sense in their own right? Again, I can say yes, they do make sense, because you can't see the typing rules here, but the typing rules are very simple, and they fit on a slide. I had to shrink it down a little bit, but they do fit on a slide. The real point is that this next A is the next step modality from linear temporal logic, and the box A type is the always modality from linear temporal logic. And this system has a really good Curry-Howard interpretation. It's a natural deduction calculus for linear temporal logic. If you care about the details, it's actually a modal mu calculus. And So the point is that just as we can understand typed functional programs as proofs, these are proofs about temporal properties. And this is an intuition you can explain and has like a real meaning aside from the implementation. It just so happens that following the structure of temporal logic also gives us a good implementation strategy. And at this point, like again, I was feeling pretty good about myself, with myself. Like I was thinking, okay, reactive programming is Curry Howard for temporal logic. That's really great. I can like pick faster, better, and cheaper, all three. The language is expressive, it's efficient, it's easy to implement. I just win all day long. But why doesn't anyone use this? And okay, so let's see why not. So here I'm going to give you the type of streams in temporal logic. So a stream of A is this recursive type, mu A times next A. So what it's saying is a stream is a stream of A's is an A today together with a computation that will give you another stream tomorrow on the next time step. So if you want to examine this stream, you have to do something at every time step. And now yes?
An alpha?
Yes, it should be next alpha. Okay, so Rowan Davies pointed out that there's a typo in the slide. This bullet A should be bullet alpha. Okay, so the thing is that this type is telling us to perform some computation at every time step. And now here is a typical GUI application on my laptop. This is Emacs, the editor for middle-aged computer scientists. And the key feature of this editor is that it is currently not doing anything. And because I'm on a laptop, I really, really want it to continue doing nothing until like I finally get tired of not doing anything and type a key. So I want this program to not execute and do nothing until an event actually happens. And this type right here of streams forces you to do something on every time step. And so if you implement it, then you have an interactive program that's awake and living all the time, which for many GUI apps is not what you want. For video games, this reactive programming model works really well, and in fact, games programmers have invented it. They call it immediate mode GUIs, and it really is, you wake up the program 60 times a second and redraw everything. And in that problem space, the kind of FRP model I showed you on the previous slide works great. But for the programs I use every day, there are problems with this LTL interpretation of reactive programs. Namely, it's like much more energetic than I am. And so now that you come back with this idea of I don't want the program to do anything most of the time, this callback structure makes a lot of sense. So we install callbacks in a table, and then with this call to get event, we block and do nothing at all until an event actually happens. And so the API to install these events usually looks something like widget.onEvent, event arrow unit. So this, come on, can you see this? Yeah, so we'll install the callback type, event arrow unit, and then it'll have the side effect of updating this table right here. And now that you think I don't want my program to do anything, this is an API that makes a lot of sense. So let's look at this type some more and see if we can actually get some structure out of it. So the point is that, like, despite doing all this work in type theory, we don't implement things this way for a good reason, but it will help to think in terms of temporal types about how GUI APIs are structured. In particular, think about these event handlers as functions that we don't call until an event happens. So that means, in particular, that we don't know the time that the callback will be invoked on. So this callback might be called at any time in the future. So so what we'll do is we'll say, okay, let's use the types that we have from this reactive analysis and add them to this type. So what I'll do is I'll say, okay, let's put a box on this type to say box of event arrow unit to indicate explicitly that this type should be callback should be something you can invoke at any point in the future. And next, what I'm going to do is I'm going to say, you know, this callback handler thing, event arrow unit, it really does look like a kind of continuation type. So if you look at it, you think, oh, that looks a bit like CPS. So let's rewrite arrow unit as not. So first, let's take that first arrow unit and make it into a not. And then we'll make the second one into a not. And now you say, okay, the type of on event is not box, not event. And if you're familiar with modal logic, we know what not box, not a is. It's the classical encoding of the eventually operator. So it's not the case that we always don't have an event, so eventually we're going to have an event. Yes?
Didn't you have eventually before?
So in the calculus I showed before, I should have had the backup slide about this, but maybe I can try typing it on the fly. So we'll see how well this works. How well this works. Okay. XB. And now, oops. So what we did before. Let me make this bigger first. Okay, so before we didn't have eventually as an operator in the calculus. We had next and we had recursive types. So what we can do, this is actually a really good question, and I should have had a slide about it. What we can do is we can encode eventually A as a recursive type. So we can say eventually A is a recursive type that either gives us an A right away or tells us to wait and try again on the next time step. So what we're doing right here is we're saying we can define eventually A as a little process that we can pull on every time step. And semantically this is a good type, but operationally again it doesn't work because it's saying pull until you get the A. And it's that pulling that's precisely what we want to avoid. So we can implement eventually in the original calculus, but it has the sort of wrong operational behavior. And so this other encoding of eventually by the classical encoding of it as not box not, that does have the right operational semantics. It says here is a function and then do nothing until the event actually happens. So the thing is that if you're familiar with modal logic, then you know that the box operator is a comonad and the diamond operator is a monad. And so you may think, okay, this just looks like a use of the continuation monad in a kind of temporal setting. Do we gain anything from this? After all, even JavaScript programmers systematically exploit the structure of the continuation monad. So when they write interactive programs, they have this data type called promises, which is fundamentally this kind of CPS thing. And in the promises API in HTML5, we have hpromise.resolve, which is the monadic return, and promise.then, which is up to some weird coercions, the monadic bind operator. In fact, the JavaScript standards committee attempted to fix promise.then so it was the monadic bind operator, but like JavaScript programmers fought back and won. So it's something else that does some implicit coercions. But the thing is that the eventually modality is more than just the CPS monad. the eventually operator in temporal logic that we can consider adding to a reactive language. So for instance, if you have two eventually, so an eventually A and an eventually B, then this implies that either A will happen first, or, whoops, oh, there should be a diamond on the outside of this, or B will happen first and we'll have to wait for A. So right here, there should be another diamond.
Before the parens?
Yeah, before the parens, there should be another diamond. And then you'll say, eventually you will learn that A happened first and you still have to wait for B, or B happened first and you still have to wait for A. And what this is doing is, this is an axiom that characterizes the linearity of time. And there is some weird modal notation for this, like S4.3i or something like that. I don't remember. So modal logicians number all of their systems. What?
This looks almost like a twisted derivative.
Yes, so at Tidy, Jennifer Pakin, who is one of my collaborators on this project, gave a talk about some of these things. So the question was, hey, this looks like a derivative, and the answer is yes, it does. And Jennifer Pakin, who's a collaborator of mine at the University of Pennsylvania, has been investigating this. And the thing is that this axiom is something that programmers are already aware of. They call it select. And it says you have two events, select the first one that happens. And the thing is that the usual implementation of select says, give me an eventually A and an eventually B, and I'll eventually give you either an A or a B, and you lose the other one. And one of the benefits of having the type theory around is that logicians have thought very hard about what the axioms of temporal logic should be, and we know that in fact we should set things up slightly differently, where we say what the which one resolved first and how to continue waiting for the other ones. And there are other operations. We can implement. So we can actually implement select. The implementation of select looks more or less like what John Reppy is well aware of. Is he in the audience? Yes, he is. So he implemented concurrent ML the underlying implementation of all these primitives looks very similar to all of that, and because that was an implementation of concurrency based on continuation passing style, and a lot of the fundamental weighting primitives were all again implemented with higher order state. I won't show you the implementation of select because it's a little too big to fit on one slide, but I'll show you some other operators that both programmers and logicians are aware of. So, for instance, here's a distributivity axiom, which says that if eventually you always have A, and eventually you always have B, then eventually you'll always have A and B. And this is called sync, and operationally what it does is it says, wait for A and wait for B, and then you'll eventually have both of them. And we can implement it. So remember that this is all going to be implemented in a sort of continuation passing style. So here we have sync, and it's going to get in a pair. One is a double negated A, and the other is a kind of double negated B. And now we want to have a double negated A times B. So what we're going to do is we're going to say, okay, first, we're going to get this continuation to which we want to pass the A and the B. And now we have to wait for A and we have to wait for B. So what we're going to do is we're going to allocate a reference cell, which is empty, and then we're going to invoke both EA and EB with a continuation, with a callback. And the callback for A will say, if when you get the A, look inside of R. If R is empty, then update it to say that you have an A now, and pass it and stick in the A that you got. And if you look inside of R and find that B has already fired, you'll have a B. And so now you can set R to done because you have both the A and the B, and you can invoke that continuation with A and B. And symmetrically, what you can do is you can say you can attach the callback handler to B and say look in the reference cell R and I check if it's empty, put B into it, and if A is already inside of that reference cell, set R to done, and then invoke the continuation with both the A and the B. Yes, Sam.
You say it requires higher order state. That's not clear.
It's not clear, but the applications I want to use it for are binding it to things like JavaScript libraries, and the underlying APIs expect higher order, like these kinds of callbacks. And so once you're in this world, it's a very natural implementation strategy. So I should say implementing it is natural with higher order state. Yes.
I don't see why you need the always A and always B. You just say eventually A, eventually B.
Yeah, so the question was, I don't see why why we have to have an always A and an always B. Why can't it just be diamond A times diamond B to diamond of A times B? And the answer is that all of these values are good at particular times. And if you have an eventually A, that might resolve at time 15, and the eventually B might resolve at time 20, and so you have to carry the A forward until the B is available, or vice versa. And that's only possible for stable types.
Another way of saying that is the monad is not strong.
Yes, that's right. Rowan Davies said the monad is not strong. That is correct. John Reppy. Why not use select?
Yeah, use select and whichever one you get, then wait.
Yes, you can. John Reppy said, why don't you use select? And you could, but I want to talk about how to implement it. And this is a simplified implementation. So the implementation of sync is a little bit simpler than the implementation of select. And so it fits on.
I meant to use select and implement sync.
Use select to implement sync? Yes, that works, but I didn't because the same difficulties arise in implementing sync this way as select, but it's simpler. And the point is that this is sort of an obviously correct implementation. Like everyone I've shown this to has said, yeah, that's clearly correct. And if I'm lucky, they say, oh, this would make a good challenge problem for verification. And if I'm unlucky, they say, what do you mean you haven't proved it right yet? Are you maybe a little slow here? So the thing is that we really expect this kind of language to terminate. So we have a normalization result for LTL, and so we expect this to carry over to our implementation strategy in terms of higher order state. So we're compiling terminating language down into ML, basically, and so we expect all of our original programs to terminate. But our implementation uses higher order state. And even though the implementations are obviously correct, we can't prove it yet. We can prove that it's type safe, but we can't prove that it terminates. So we used step index logical relations before, but they don't seem to scale to this kind of liveness problem. And so we need new techniques. And so this is really one of the big punchlines of the talk, which is that, you know, we've been driven towards sort of a type theoretic reconstruction of traditional techniques for implementing reactive systems, and now we have like very strong reasons to believe that these traditional implementation techniques are not just correct, but are actually extremely well behaved for like this for well-typed programs. But we can't quite prove that the implementation is 100% correct. We actually actually need new techniques to do this. And so this is actually extremely exciting because, you know, ML is like this old higher order imperative programming language from the 70s. And, you know, everyone is really excited about FRP, and now, you know, it's Curry-Howard for LTL, and it's like efficient and realistic, and it's purely functional and easy to reason about. But to implement this, we need to understand ML. So there are important lessons still to be learned from ML, like, you know, even decades after it was Robin Milner decided it was a good idea. And so this is sort of the lesson for the ML workshop, is that, no, we still need to think about ML, like not just in the context of concurrent systems, but like, you know, plain old sequential ML has a lot of mysteries to it still that we need to understand. And if we can understand them, like the techniques we need here, we should actually scale to doing things like proving liveness of concurrent programs, which is, you know, one of the big challenges of today. So like there's a lot left to be learned, and that's really the main message of this talk. Thank you.
Yes, your model typing seems to be related with the synchronous hypothesis that was developed with the French school of synchronous programming languages. So what does it relate to this?
So the question is, how does this model relate to the synchronous data flow paradigm developed in France? And the answer is basically this is so there's a family of languages like Lucid Synchrone and STRL and things like this, which are actually really impressive. Like you give these recursive stream equations, and then it gets compiled to a state machine, and they use it to do things like control trains and fighter planes and things like this. It's really impressive work. And the way to understand this is that the work I'm doing can be understood as a sort of higher order version of synchronous data flow. So when we move to higher order, we both gain and lose some things. So the loss is that this synchronous data flow in the French style can be compiled to state machines that don't allocate anything. And so you have like super precise resource bounds on them. And we lose that with these higher order functions. But on the plus side, we gain the ability to do like sort of dynamic data flow graphs. And if you look at a GUI, like windows come to life and go away all the time. So it's necessary to model those kinds of things.
So you asked at the beginning of like, well, why don't people use these kinds? Let me propose an answer on this. And the answer is that, in some sense, the traditional FRP view is sort of approaching the problem the wrong way, in that it thinks of the GUI problem as being one about, fundamentally about expressivity, about making a nice way of expressing programs about time. And the answer is actually most of the problems in GUI programming, including the one you showed on your slide, aren't about time, they're about consistency. And instead what people do, and in real world this is with React and Elm, is say, no, what you need to do is keep your state as a simple pure type, have your view as a function that renders that type, and then we'll have some like concurrent stuff that happens on the side which updates the model using ordinary concurrent programming techniques. And just like that, just reactive programming is not time-oriented programming. Now you can think about, instead of how to integrate time, think about how to optimize that function. Where you use all sorts of techniques, including self-computations and stuff, but then time doesn't enter into it. So I'm wondering, what do you think is compelling about the time-oriented view over this kind of simpler, just like optimization?
Okay, so the question was that tell me if I'm rephrasing you incorrectly. So if you look at language libraries like React or languages like Elm, they have a model where you view your data, your GUI as basically a document tree, which doesn't change. And then when an event happens, you build a new representation of the GUI, and then use some clever concurrent techniques like tree diffing and things like that to update the GUI. Is that more or less correct?
The more important part is the way you think about handling of state is have some abstract programmer controlled data structure. This is what the state of the application is. And then you have a pure function. It goes from that to the view, which happens to be some hierarchical thing, but that part almost doesn't matter. But the key is this view function and all the consistency problems as well.
Okay, yeah. So the idea is we represent the like sort of we represent the state explicitly and then render it and have a rendering thing. And yes, so that the way I think about this is that that model mostly works but doesn't quite, because like a lot of the hard problems have been shoved under the hood when you say, oh, we have an abstract state, because we actually want to build user interfaces in a modular way, which means we need to build up that state compositionally, and that I find is difficult when you view the interface as like a state machine evolving over time, because you have just a single state and you don't have as many techniques as you'd like in order to structure that state. So the thing is that at a fundamental level, a stream is a representation of a state machine, and what these reactive abstractions are essentially giving you is a story for how do you put these state machines together in a systematic way. And like, I think that's actually an important thing to have. Yes.
So you mentioned that you don't have termination proofs for some of the for this, but do you really always want termination? Like if you were you had a server or something that was constantly running, really would I imagine want termination? So
it's
work like for that kind of thing.
Yeah. So the question was, do we really want termination? And the answer to that question is, well, there's two answers. The first is I do.